Good afternoon, ladies and gentlemen. It's my pleasure this afternoon to introduce Dr. William Lahoz, who is visiting our group in ACD from Nilo at the moment, or Météo France? Nilo at the moment. So William's an expert in data assimilation, and we've been working together over the last few years because we share an interest in trying to take monitoring of air quality to geostationary satellite, using geostationary satellite observations, and we've been doing some of the work using observation system simulation experiments to try and show what capability we might be expect if we're able to do this finally. So William at the moment is a senior scientist in NILO, that's the Norwegian Institute for Air Research, and there he leads data assimilation activities across a broad spectrum of the earth sciences. During the last few years, he's been a visitor in Météo France, and this is where we've been working on some of this joint interest in geostationary remote sensing. Now, prior to moving to Norway, William was at the Department of Meteorology at the University of Reading in the UK, and he co-founded the NERC Data Assimilation Centre, DARC, which is one of the two Centres of Earth Observation Excellence in the UK. He has also led prestigious EU and ESA projects on data assimilation and set up various summer schools. And he's also lead author, co-editor on a Springer book on data assimilation. This afternoon, William's going to talk on data assimilation, making sense of Earth observations. I'd like to welcome William Lahoz.
Right, David, thank you very much. And I've been here, it's not the first time I've been in NCAR. I mean, I was here more than 10 years ago when most of you were at Table Mesa Drive. And it's still a very nice place to visit. And I'm quite impressed by your sort of facilities, especially for visitors. I have been here for about 3 weeks. And as you can see from here, I haven't just been sort of collaborating with David's group. I've also been finding out the wonderful Southwest USA, and that you can identify as Monument Valley. And I took the picture. I don't know if it's a great picture, but I like it. And it's a testament that it's a great part of the world to sort of visit and not just work, but have some good times. So with that, I'm going to try and talk to you about data assimilation, making sense of Earth observation or observations. I want to try and sort of guide you through how I understand what data assimilation is about in a way that hopefully is not too sort of painful. If you want to sort of get in touch with me for any reason, that's my email address. And if for any reason you perhaps don't understand what I'm saying, and in fact you want to find out more, there's this book from Springer from 2010, which I'm the lead editor. And it talks, in fact, the title is something like Making Sense of Earth Observation Data Assimilation. Okay. Before I plunge into sort of the details of data assimilation, I'll provide you with some thoughts. Now, the Chinese here, I'm not an expert in Chinese, but I've been told by a colleague at NILO who knew Chinese that this is correct. If it's not correct, well, you can tell me later. But I think this is relevant to what I'm going to tell you about, because how we find out about the world around us is there are a number of ways. And this gentleman, Confucius, well known, he had 3 ways of doing that. For learning wisdom, in other words, finding out, understanding what's out there. First, by reflection, we can do that. We can think about the world around us. He said it was the noblest way of doing this. Imitation, you can find out what someone else is doing. It seems to work. I'll do that. That's the easiest. Or third, by experience, which is the bitterest. Something may happen. It could be the sense that there perhaps a hurricane comes, Sandy or something else, and there's devastation. And it's not just a social cost, but economic cost. And these things make you think, well, what can I do to try and sort of alleviate this, find out more about this. That's the third one, bitterest. The second point is that I don't think we should sort of assume we know everything. I think that would be incredibly dangerous. We would have to sort of say, we have to be humble and say, I want to find out about the world around us. I'm going to sort of say, I don't know all the answers. And I want people to question me. And that's a way of finding out more what the answers are. So that's the second point. And the third point is that often, when we're going to try and do something that is quite grandiose, we're very ambitious, we should sort of start small and build things steps by steps. And that's the third point about, if you want to build a mountain, you start by carrying away small stones. So hopefully, I think these three sort of quotations from Confucius convey to some extent what I'm trying to tell you about Earth observation and data assimilation. This is the outline. I'm going to tell you about the need for information, why we need information. I'm sure that the examples I will give you, you will be aware of them. But nevertheless, I'll provide them to you. I'll then talk about observations and models as sources of information, and I'll focus on what I regard are their key characteristics, and that will allow me to introduce data assimilation to you, hopefully in a rather sort of natural way. I'll then talk about data assimilation. I'll go from the side, I'll provide some sort of basis for the mathematics of it, so that provides some sort of foundation to what you're going to do. Amongst other things, perhaps you can sort of provide proofs that you're getting the best estimate of the atmospheric state. And then I'll provide hopefully a demonstration which is compelling of how data assimilation adds value. And I'll try and say what I mean by adding value. I'll then proceed to provide 3 examples of data assimilation. These are not exhaustive by any means, but I'll talk about chemical data assimilation, but assessment of new observing systems, and this is where the link with NCAR comes in, and land data assimilation. I'll then go on to an outlook for data assimilation. Again, it's not exhaustive, but some examples, some recent algorithm developments, for example, in numerical weather prediction, in particular ECWF and the Met Office. And I'll provide what I think could potentially be a rather exciting application of data assimilation into what is called a citizen observatory. And if you don't know what it is, I'll let you know what it is. You'll find out later. Finally, I'll pose the question, what did data assimilation ever do for you? And I'll provide an answer of that, hopefully. We need information. The main challenges to society require information for intelligent response. And we need that information to make choices in future action. Examples include climate change. Here's from a recent issue of BAMS to do with climate change. What was State Climate 2012. So based on that, we're going to try and find out what we can do about it, what we need to learn to sort of tackle what's going on. Impact of extreme weather, environmental degradation, issues like air quality there, again, the link with NCAR, ozone loss. And this is ozone loss there. And, of course, there are the requests for information. I think, I'm from the UK, and most of you are from the US, and these 2 countries have a particular sort of liking for finding out information about their citizens. So it's not just about science, but I think other sort of groups. And I think I was thinking of an acronym for NSA, and it's the Numerical Systems Association, which are actually very keen on finding out more about you. That aside, we can take action according to the information obtained. And it's not just enough to get information, you want to do something with it. You might wish to sort of find out what the future behavior of the system of interest, which could be their system, for example, the climate, future events. You want to do predictions. You want to have an algorithm that will give you predictions, which you can test against observations. And in fact, one might argue that's what, for example, physics is about. You make predictions and you test them. And if they don't pass that test, then you try and sort of find out a different way of describing the world around you. You may wish to test understanding of the system and adjust your understanding, or perhaps doing hypothesis testing. Typically, you would use a model that embodies your understanding of the system. Last but not least, and again, not exhaustive, you may wish to assess the system, for example, air quality regulations. So you would like to monitor what's going on. In order for that, you need information, which can come from observations and or a model. This is from the BAMS for State of Climate 2012. You don't need to sort of look in detail, but select notable climate anomalies of 2012, and we're in the US. So from this, there was a drought in September 2012. And I think it was, it's not just a question of you're interested in it from a scientific point of view. It's not just a question that it's a social interest, but it's economic interest as well. resulted in multi-billion-dollar agricultural disasters. So this information is not just because you're interested in finding out something that you might find interesting, what is causing the drought in the US and how perhaps you can monitor it a better way, but these things actually cost money. And if you provide information to the policymakers, they can do something to try and sort of make sure that you don't sort of lose as much money as you did hitherto. One thing I will point out is that where I live, Norway, nothing happened. So perhaps it's a rather boring place, although, I mean, sometimes it's good to live in a boring place. But that aside, all these things are happening, and this is just part of about a quarter of the world. I mean, there are things elsewhere. These are things that affect you, me, and other people, and affect society. And it behooves us to get information to tackle these things. And one way of doing this is to getting through observations, and then also through models that embody our understanding. And I'll go on about how to bring these two together. But another thing, this is more for Europe, the side of concern health and economic cost. In 2003, in August in particular, there were very high temperatures in Europe. Actually, one of the ironies here is that these temperatures were comparable to the temperatures you normally find in North Africa. But these temperatures in Europe one really cannot cope with them. Also, I think people are not used to them. The services, the society is not quite set up to deal with them. But the point of this is that there are quite a lot of deaths, particularly in France, of the elderly. And associated with this, there's a big health cost. And when you look at the health cost of things like high ozone, which in the troposphere, which is a pollutant, people being sick and so on, and a number of other factors, loss of life, whatever, and when you cost that, it's in the billions of euros. And if you are in the US, of course, it'd be billions of dollars. In the British newspaper that I look at electronically is The Guardian. Today said there's an article in Nature, and it's talking about a number of cities in the world, including Miami, that would be in danger, I think, of flooding with climate change. And the amount of the economic losses there will be ordered at trillions of dollars. So these things are not just important from a point of view of science, society as such, but also from a point of view of economics. So if we want to find out about the world around us, we have to find out what are the sources of information, what can help us find out more about the world around us and make informed choices. So observations, we have in situ, for example, they're ground-based, ocean sondes or normal sondes, buoys, aircraft, and so on. They have some features. They are sort of they tend to be local in the spatial scale and temporal scale. They're very, very short, sort of made over short temporal spans. They're not global, so that's an issue. Or you can have a satellite. It could be a geostationary satellite or an Earth orbit satellite. They have their own advantages and disadvantages, but the main thing is that the GEO is not global, of course. It's you cover about a quarter of the Earth, but a LEO, it's almost global. But then the temporal sort of the temporal resolutions are different. You have a very high temporal resolution from a LEO. From a LEO, you don't have as high a temporal resolution. So these observation types have advantages and disadvantages. One of the things that one would like to do, in fact, people do at numerical prediction centers, is to combine this information to try and make use of all these advantages. And I'll tell you how they do this, so that you can guess how it does that. You can have a prior knowledge of the Earth system, which, again, going back to what Confucius said, you could have a reflection, you can think about the world around you. What do I think is causing this or that? Use imitation, find out what someone else is doing. Oh, this be useful. Or experience, find something happens, you learn from that. So that would be observations. And you can embody this understanding in a predictive algorithm, which we commonly call a model. And that model can be as simple or as complex as you wish. So what are the key characteristics of this observational information? And this is hopefully going to lead me into introducing data assimilation. Well, of course, they have errors. Information has errors. The errors are systematic. You call a bias, random, so the precision, or representativeness, which means that you are trying to represent information at a different spatial scale than for which it's sort of designed. In the example I give, if I give you the temperature at the middle of this room here, and then I try and say, well, that's the temperature of the whole room, then I'm making an error of representativeness there because I'm going from a point, so sort of a source, to something that's of the order of several square meters. But a key point is that observations have gaps, both in space and time, so they're spatial temporal gaps. And I'll show you in the next slide. you would like to fill in those gaps. This is also true for model information. Models have spatial temporal resolution, and it says they have gaps, although you have, through the model, through interpolation, you could go to the resolution to find a resolution, although things may not be applicable at that resolution. Okay. This is where I would like to sort of start introducing data assimilation. This is an example of MIPAS ozone data, 10 hectopascals, 30 kilometers on the 23rd of September 2002. So the southern hemisphere, that's Antarctica. Blue is low ozone, red is high ozone. The key thing there is that this information has gaps. And that is true of all information. Okay? You're not going to cover everything to any scale you wish to do so. So observations are discrete in space and time. You may say, so what? Well, so what? I may wish to find out the value of ozone between those orbits. Why not? I'm maybe interested in this place over the world. This is, I think, Rio de Janeiro around there. I may wish to find out that. Also, I may wish to grid this information, because if I grid it, I can do some things with it that are harder to do if I leave it like that. I may wish to calculate some flux. I may wish to quantify things, integrate these quantities. I may wish to compare against something else. If I grid this information, it's much easier. So the question is, how do I fill in these gaps? Now, the simplest thing I can do is actually do a linear interpolation. And this is where I say one thing, that all of us have been data simulators. I'm sure in your life, you have done some linear interpolation for the data that you have. And in doing that, you have assumed a model that the information between the orbits, in this case, varies linearly. It's a very simple model, but it could be a very useful model, in particular if these observations are very close in space. The key point here is you need information to fill in the gaps. You need a model to fill in the gaps. Now, what model you use is up to you. I say I could use linear interpolation. Okay. But I could go further. This is ozone. I know what the chemical reactions of ozone are. I know that ozone is moved around. I have the transport equations. I could use that, and I could use the chemistry transfer model. My chemical reactions can be as simple or as complex as I like. I could go and say further, well, I want to do this for the atmosphere. Since the 19th century, we've known what the Navier-Stokes equations are, how they determine how the motions in the atmosphere. I can incorporate that into a general circulation model and use the general circulation model to do that interpolation. So that's what data assimilation pictorially is. You are filling in the gaps in the observations that they are in space and time and using a model. And you also take account of the errors. And the model is up to you. But what we can do is try and find out a way in which we combine the observational information and the model information that is, in some sense, this objective, and in some sense, provides the best solution of the state that we wish to find out. And that's where the mathematical foundation of data assimilation comes in. It's an objective way of filling in the gaps by melding information from observations and models, plus the errors, and plus mathematical foundation. There's a number of ways in which you can go about it. You can look at the Bayesian approach. Here, what you're doing, you have a priori, you have information here from observations. It's a departure from the analog from a model, given the state of the atmosphere, for example. And here you have a priori information of the atmosphere. You're combining that probability distribution with that probability distribution plus a constant, which is there to make sure that things are normalized, that the probabilities don't exceed 1. And here is what you want. You want to find out the likelihood of the state of the atmosphere. It's not. From a deviation from a background state, which embodies your a priori information, what you knew from before, given that you have an observation and it deviates from the model analog of that observation by this amount. And there you have it for different times, for different time steps. Typically, this would be for a variational method where you take account of space and time. So that makes sense. I have information from observations. I have information from my priori knowledge, we embody the model. I combine them, and I want to find what's the posterior likelihood of making a measurement, of finding out about the state of the atmosphere. Example is here. So the two approaches of doing this, statistical linear estimation or ensembles. E and KF is the ensemble Campbell filter, and PF is the particle filter. Two examples of the statistical linear estimation are variational methods. It's going to be 3D var if you exclude the temporal dimension, or 4D var with the temporal dimension, or sequential methods, typically the Campbell filter. When the system is linear and there's a Gaussian, in standard linear statistical linear estimation, you get Bayesian estimation, and also you get the best linear and bias estimate, the blue. People talk a lot about the blue in data estimation. And mathematically, this is what they are. This is the variational methods, var. This is a penalty function. This is actually for 3D var. You have here, XB is your a priori, embodies what you knew from before. It's your background also. Y is your observations. X is what you look on to try and find out. And you actually have to sort of wish to sort of find out the difference between the observations and what you're trying to find out would sort of give you in this space of the observations. And then you have to weight it by the inverse of the error covariances. This is for the background, for the measurement. That's a variation method. It's a penalty function. You minimize that. The minimum will give you X. All very well and good, mathematically, and to pose it, but it's actually very difficult to find that out. If this is not linear, you're not guaranteed a unique minimum. Furthermore, if you look at numerical weather prediction, the state vector that you wish to seek for has 10 to the power 7 elements. So these matrices are of the order of 10 to the power 14. It's extremely difficult to invert a matrix of that size. So you need to do something about that. This is a sequential method. Similar things. This is a forecast. This is a model that involves analysis to the next step. This is the error. This is the analog of B. But the fact that it's different is here, it's because in the sequential method, it's evolving in time. Typically, in the variational method, it doesn't evolve in time. This is a model error, which is something that you introduce as well, because you not only have error due to initial conditions, but you also have error because the model is not perfect. And then you have the analysis. This is what you want. There's a forecast plus some deviation from the observations, and the common gain, which is that, and you have analysis of the error covariance of the analysis. These things are equivalent under linearity. So these are the mathematical equations. I don't think I'll have any more mathematical equations here, but the reason I'm showing this slide is that it's not just about sort of saying find things. I want to combine an observation and a model, and this will give me the best result. So it's actually, you can use the mathematical apparatus to show that what you're doing, is the best thing you can do. Admittedly, you're going to do so many, likely to do a lot of approximations. That means some of these conditions of optimality will weaken. But in principle, this is the best we can do, and there's a mathematical sort of foundation for what we're going to do. Okay, added value. You may have heard, perhaps even from me, that data assimilation adds value. And you'll say, well, what does he mean? Or what does she mean if it's a lady talking about it? I'll try and convey this in this particular slide. You have seen this. These ambiguous observations of ozone. With all the features that I said before, spatio-temporal gaps. Okay? I can fill in those gaps. And how can I do that? I can do that using a model. And I can provide a 6-day forecast for that condition. This is actually from the metals. Okay. What is happening here? The 6-day forecast is going over the sort of limit over which we are sort of going to be constrained by observations. In fact, the model here, the forecast, is giving you basically the normal ozone hole over Antarctica. This is the model, so that's, you say, the typical parameter space of the model, which is nothing wrong with it. It's consistent with the model, with its own space, but it's not what happened in reality. Because what happened in reality, I mean, I think any of you that has worked in this strategy will probably be familiar with this event. It's about just over 10 years ago, when the ozone hole over Antarctica split into two. In fact, it was quite interesting, and there was a lot of sort of excitement about it in the community. The point is that the observations have gaps, don't quite capture that, although you can see an inkling of that. The model fills in those gaps, but it doesn't quite capture that event either. So you need to combine those two using data assimilation and errors to get that, which is what actually happened. So data assimilation adds value to the observations because it has filled in those spatio-temporal gaps. It adds value to the model because it has constrained the model with observations and kept it within the rails with reality. And you get an analysis, which is what happened. Or so you think, because it doesn't end there. This is an important point. You get an analysis. You shouldn't just say, oh, great. My work is ended. In many ways, it just starts. Because what you need to do is to evaluate that in a number of ways, including looking at self-consistency, which I'll talk a bit about later, and comparing against independent observations. In fact, when you compare against independent observations, some from SONS and so on, that's exactly what happened. So data assimilation gave you a good estimate of what happened in the atmosphere then, and neither the model nor the observations gave you that faithful picture. And data assimilation added value to the observations and the model in the way I've said. Let's say, okay, yeah, where else has data assimilation been useful? Okay, people joke about the weather. In fact, this morning I was reading there's some 10 rules. I think it's Elmo Leonard who died recently. He died yesterday, and he said he had 10 rules for writing a novel. One of them is don't start with the weather. Okay, but regarding the weather, this is ECNWF. Likely, if I may say so, perhaps the best numerical weather prediction center in the world. This is an example of the success that data assimilation has had in the forecast. This is actually forecast. This is a normal correlation of the 500 hectopascal height forecast for the extratropics. So they exclude between 20 south and 20 north. This is 3-day, 5-day, 7-day, and 10-day forecast. And this is time. The top line is for the northern hemisphere. The bottom line is for the southern hemisphere. So things to point out. First thing, guided by these arrows. So in 20 years, the accuracy of that forecast has increased by 2 days. It may not seem a lot, but it's actually a lot. And in terms of economical impact, it's quite a lot. So that's mainly, it's not just, but a lot of that impact comes from data assimilation. Another thing to note is that these two lines, say for 3, 5, and 7-day forecasts, have come together. So what's happened? What's made them come together? Well, the reason that they've come together is because satellite information has been increasingly used for data assimilation both in northern hemisphere and southern hemisphere. Before that, it was mainly sort of ground-based data. That's buoys, aircraft, so on. Of course, the southern hemisphere, being largely ocean rather than land, there's less information of that ilk, like from SONS and so on, of ground-based. So this shows how with satellite data, the skill of the forecasts in the northern hemisphere and southern hemisphere has become comparable. The other thing that happened in 1999, I've circled that, is that a more advanced version of 4D VAR, 4-dimensional variational method, was developed. And also there were significant changes in the global observing system. You shouldn't come out from this slide that it's just data assimilation that's done this. It's been a combination of many things. It's been data assimilation, better observations, higher computing power, better models, better sort of modeling of processes. But all these things together, data assimilation has been very important in giving you an improved forecast. The other thing I'll say, you may not believe the weather, you may think that weather forecasts are rubbish, but almost certainly, when you fly, and certainly most of you, all of you fly, if the sort of system goes into an autopilot, they're likely using concepts of control theory, which is very much related to data assimilation. So if you don't trust the weather, I would hope at least you do trust the airplane you're on when they're on autopilot. Because if you don't trust data assimilation, then I suggest you don't fly. Okay. We know about, hopefully, that we need information, that their observations and models, they have errors, and have spatio-temporal gaps in that information. One way of bringing this information together is through data assimilation. I think it adds value the way I showed, and also it's an objective way of doing so, and you can sort of provide a mathematical foundation to the way it does that. I'm going to provide you 3 examples of data assimilation. They're not exhaustive by any means, and the ones with which I've been involved with in work. So first, about chemical data assimilation, an example of evaluation of ozone analysis using self-consistency. This is not enough to tell you that actually your analysis is correct, but it's a necessary condition. It gives you an idea that your analysis may not be correct, that you may be doing something wrong. At the end of the day, the final arbiter of whether your analysis is correct or not is comparing against independent information. And what I mean by independent information is information you have not used in the data assimilation process. Also, make an example of analysis of data transfer, so mapping, this analogous to doing comparing against independent data, and also of evaluation of assimilation approaches where you use a model like a DCM or a CTM, or you use a rather simple chemical scheme or rather more complex chemical scheme. I'll go on to talk about how to assess new observing systems and introduce the concept of the observation system simulation experiment that David mentioned earlier. And I'll say a few things about geostation missions to monitor air quality. In this case, about ozone and carbon monoxide. Ozone is important for chemistry in the troposphere. It's also a health hazard, it's a pollutant. Carbon monoxide, it gives you information on transport processes because of its lifetime. As I talk about land data assimilation, of course, it's different in some respects from the atmosphere, but it's also instructive because it gives us different challenges. And I'll say a bit more what these challenges are. And in fact, it does happen that in Norway it's rather challenging for land, and I'll try and say a bit about that and provide some sample results. Okay, chemical data assimilation, self-consistency. One of the things that one does in data assimilation is assume that errors are Gaussian. It's not an unreasonable thing to do. I mean, in the absence of any information, the best guess you can make about the PDF of anything is that it's Gaussian. Okay? But also, if it's Gaussian, some very nice properties associated with these distributions. So often when you start a data assimilation scheme and you assimilate observations, you assume that the observations and the model have Gaussian errors. You can test whether this is the case by looking at something called the difference between the observation and a short-range forecast, OMF. If your errors in the observations and the errors in the model are Gaussian, this difference, OMF, should be Gaussian as well. Here, this OMF has been calculated. First for a Gaussian fit, so where red is the free model and black is the data assimilation, and for a system called BASCO, which is from colleagues in Belgium. We basically use the 40-bar with the CTM. For 4-6 species, this is 0. And what we find is that, in fact, and this is normalized as well, find that basically the black curves for data assimilation are centered around 0. So they have not much bias. So the observations and the forecast are close to each other, which is what you would expect from a well set up system. And also Gaussian. For the red, you find that in some cases they're off 0, so there's a bias. So the observations on the model without data assimilation and the observations don't agree well. And in some cases, actually, they're quite flat, which might sort of suggest that perhaps it's similar to Gaussian, but it's less peaked than here. So you say that your results, so the analysis results show that they're consistent with the Gaussian errors assumption, and they show added value. The assimilation is closer to the observations than the model. You may say, well, so what? But if you don't get that, then you're not doing it properly. Because when you combine the observations and the model and do that besides the model, you're adding information to that system. So you should do better. If you don't do better, there's a problem. And in fact, there's some cases in which you add information to a system and you do worse. Often this suggests that what's happened is you've tuned your system to do something, which works in some cases, but it doesn't work in other cases. So this is self-consistency, checking things like Gaussian errors. This is another aspect you want to evaluate MIPAS ozone data called OBS1 using essentially independent data. So use the assimilation, the analyses, in this case from BASCO as a transfer standard. So what you're doing is actually doing this difference. So OBS1 is MIPAS. You're taking the difference away from the analysis, less this difference, and of course these analyses cancel. And effectively what you're doing is you're using the analysis to map one observation type from their space into the space of a different observation type. And these observation types have different spaces. They have different characteristics. So we can do that using simulation, and this is compared against Halo 2 and so on, observation 2. And this is done for 5 latitude bins from 90 south to 60 south, 60 south to 30 south, the tropics, 30 south to 30 north, 30 north to 60 north, 60 north to 90 north. And there's the percentage difference. And in fact, what you find is that MIPAS ozone was had a generally positive bias between 5% and 10%. This is something that we could do. And in fact, I would argue that that is a much better way of doing it than just doing a simple, sort of looking at some sort of circle of radius of sort of influence, so within 300 kilometers or within 6 hours or something like that. This is doing the mapping in a better way and including more information in doing that. But this sort of thing that when we did that, we then passed on that information to the MIPAS team. So this is a third and last example for chemical data simulation. This is an ozone time series of 68 hectopascals at the South Pole. This is the ozone. This is time. This is a whole bunch of systems, ranging from GCM types, like ECWF, to CTM from BASCO. And as the ozone hole comes in, you see how they decrease. But some things to note. Although the models, the analysis basically track the ozone hole, it says that they go down. They don't quite go down to 0. Some degree of spread around there. And also with different systems, they do sort of disagree in a number of ways. But 2 things I want to point out here. The first thing is, when we first did this, this is the result that the BASCO got. Not very good. So they went back and looked at the system, found out there were some issues, some problems, and they corrected it, and then they got this. Much better. Okay, you say, well, eventually they could have done that. They could have got that and found out that their analysis had problems. But this sort of thing, using data simulation, was actually, they were able to do this much more quickly. Okay? And it's basically confronting their analysis with observations. See how well they did. The second point is this of the operation ECWF. This is here red dashed, and it was not quite capturing things. And this is red here, where you simulate MIPAS ozone. So the lesson here is that when ECWF in the operational ozone forecast system did not assimilate MIPAS ozone, with its sort of advantage of having a relatively high vertical resolution in the region over Antarctica, they weren't quite getting the ozone loss. It's only when they added MIPAS ozone that they were able to do much better. So the first thing is that this actually is very illustrative of the deficiencies that you might have in the way you have set up your operation system or your assimilation system. The other thing it also shows is that in many ways, if the transport is a dominant sort of thing determining the ozone rather than chemistry, it didn't matter very much whether you use a very simple parameterization like the carrier scheme, which is what ECWF and us dark mathematics did, or a rather sophisticated heterogeneous sort of chemistry scheme like BASCO did. You didn't get results that were much different. In other cases where chemistry is important, you might find that it might matter what sort of a chemical scheme you use. But this sort of thing allows you to test how you set up your model, how you set up your data simulation system, whether it's a good thing to have a sort of a very sophisticated chemistry scheme, or it's enough to have a parameterized chemistry scheme, and also shows the impact of including information in your simulation scheme. Okay. Assessment of new observing systems. You may, if you're interested in numerical weather prediction, air quality, or many other things, say, okay, I have this sort of set of observations, and they're giving me these results. What happens if I add a new observation type? Do I do better? And how much better I do? So one question you might have, if for air quality, you might decide of the US, I'm going to have What if I have a one geostationary satellite of the US, or I have a ground-based system of measuring ozone? So how do we quantify the added value? So you want to see how well you can monitor the ozone in the atmosphere, but also you can look at the cost. I know how much one geo costs, more or less. I know how much a one ground-based station costs. So if I have 1,000, 10,000, then I can find that cost. So what you do is you do not consider the value of the extra platform observation, but the added value of addition to what is already there. If you have a lot of some temperature observations, it's going to be very difficult to add value to that. And in fact, that's what happens in systems where you're looking at adding temperature. Satellites that measure temperature is very difficult to sort of make improvements. But if you have a system where you don't have a lot of sort of information, because that could be ozone in the lowermost troposphere, then you're very likely to do better. But what you need to do is look at the incremental value. So use data simulation to quantify additions to the global service system and how you design it. And there's a number of work by Masutani et al. And it's also related to the concept of observing system experiments, which actually you look at observations that are already there, as opposed to observations that will be in the future. So what is the setup? You have a simulated atmosphere, the truth, which you call the nature run, and you use a model or analysis to set that up. That's actually a difficult step there, because you have to try and be as realistic as possible, and one of the key things is try and test that your nature run is realistic. Then you sample this to get observations of the instruments that you're interested in. And then you consider two types of experiments, all observations plus the new type. So you want to find out the impact of the new type compared against all observations. And then you compare the performance of C1 versus C2 using, say, data simulation. So the goal of an OSSI is to evaluate the difference C1 minus T. But T is the truth, the nature run. Measured objectively, I can say something about that, is significantly smaller than the difference C2 minus T. If that's the case, then you would argue that the new observation type is actually has a significant impact and it's worth including it. One thing that is true is that there are fewer observations in air quality for the global service system than, say, for numerical weather prediction. So typically, with one that's in air quality, instead of having a lot of observations plus the new one you're interested in, against a lot of observations, you basically just have one observation type, and you compare it against the performance of a model, a pre-model run. An OSSC has a number of shortcomings that people have to be aware of. They're complex, they're comparable to the data simulation system. There are ways of alleviating this. You can sort of simplify it with a reduced OSSI, for example. You look at numerical weather prediction, instead of using radiuses, you use profiles. They're difficult to interpret. They could be model dependent. So because of that, you have to be very careful about that, how you set up the errors. Perhaps you use conservative errors and use several methods to try and assess the impact. Incest, some people have said, well, you should use that word, but it is akin to incest. And in fact, it was in a paper that I wrote as first author, and certainly your referee commented on this. But that aside, is when you use the same model for the truth and the assimilation. The problem with doing that is that you are over-optimistic in the impact of the observation type you're interested in, and you should try and avoid that. But the problem if you do that is you use different models, there could be biases between the models. So it's, the solution is not straightforward. But if possible, you should use different models for the calculating the truth and doing the simulation, but hopefully that they're not so different that you can afford to ignore any issue of biases. Despite these shortcomings, the high cost of Earth observation missions, an example here, MBSAT, which sadly no longer with us, the different sort of numbers of how much it costs. Well, one of the numbers is of the order 2 billion euros. If you're going to throw up a kit that costs 2 billion euros, it's not a bad idea to try and find out how it's going to behave. And even if it costs a little bit of money to do that, it's worth it. So that's why, despite the high cost of Earth observation missions, OSSIs often make sense to space agencies. In my experience over the last 10 years or so, space agencies, ESA, NASA, and so on, have become much more interested in OSSIs. I think more than 10 years ago, probably likely ESA didn't know what they were. And now almost any mission that they consider, they want them to do these sort of things. This is what I said before. You need to check the realism of the truth, because that is, if it's not realistic, then that will compromise your results. For an air quality, for example, the truth was evaluated against ground-based stations, so the work I did when I estimated ones. So this is a proposed mission for ESA 8th Earth Explorer. looking at thermal infrared plus visible and looking mainly at ozone and carbon monoxide. It was not. There were about 30 plus missions. Only 2 were accepted. This one was not. But there are a number of things that are positive, as mentioned by the reviewers. That's. I think it was one of the children of Bansan and Puch, who's one of the investigators that did this drawing, which some people have argued that is the highlight, the best thing for the proposal. But I mean, you can debate about that. But the other proposed geostationary missions for air quality, mainly for, I'm not aware of any in the southern hemisphere, but so these ones are northern hemisphere, so it's GeoCape and Tempo here in the US. NCAR certainly very much involved in GeoCape. There's a mission in Korea, GeoSat, and the mission in Japan called the Climate, and maybe more. And that's actually an issue that I know that people in David Ed's group are working very much is the issue of having a geostationary constellation of satellites, so one over US, one over Europe, and one over East Asia, and how that brings benefit. So there was a thermal infrared done, where we excluded the visible component, and there's a number of papers with clay metal in AMT, and it's this MAGIC instrument, and we were comparing against MTG. Note that they're MTG-like and MAGIC-like, and also that the comparison is not entirely fair because MTG is more designed for numerical weather prediction, MAGIC is more designed for air quality. But nevertheless, we did that comparison. As truth, we used Mokage, or quantum model, CTM. We simulated one observation, either ozone or carbon monoxide, and we compared MAGIC and MTG. And we studied the sensitivity to a number of things, initial conditions, atmospheric forcing, and emissions. And we looked at 2 months, July and August 2009. That's a summary of experiments. I'll show some results. What you need to look at here is the green and the red line and the black line. The green line is MAGIC-like. The red line is MTG-like. The black line is the free model run. And this is the comparison against the truth. These are 4 experiments, which are described in the previous slide. This height from 0 to 5 kilometers in the atmosphere. And that's correlation. That's the bias, absolute relative difference, and that's the root mean square. And here you want the green to be furthest to the right, and here you want the green to be furthest to the left. What you find is that, indeed, in all cases, the green line satisfies those criteria, so you're doing better. Okay? Which is good, but it's not doing so well in the lowermost troposphere, around 0 to 1 kilometer. For example, here, the difference is much lower. In fact, there may not be any difference. And this is where you need the visible rather thermal infrared. Because again, this is work that's being done in David Ed's group, also done at Meteo France and elsewhere, is the fact that you're combining 2 different parts of the electromagnetic spectrum to get a handle on the whole atmosphere to the ground. And here, what you need really is a visible component in your measurement to go all the way down to the ground. That's a summary, just reflects what I said before. Okay, this is perhaps something that here people maybe they look at the land. But I'm going to talk a bit about what we're doing in the land and some of the issues that pertain to the land. A number of challenges in land data assimilation, and many of them actually do apply to the atmosphere, but some of them are more peculiar to the land. One is the fact that you are considering in situ and satellite data, and of course there's a lot of heterogeneity in the land. So you need to sort of disaggregate data, so basically match scales from large to small in the land more than I think you're likely to do in the atmosphere. You also need to look at radius simulation, which you do in the atmosphere. Numerical weather prediction centers tend to simulate radiuses rather than profiles. You look at multiple sensors like you're doing for example, for air quality. You're combining things, different types of sort of parts of the electromagnetic spectrum. You need to, of course, look at errors and biases. But one thing you need to do with the land data simulation is the fact that it's heterogeneous, likely to be nonlinear, likely to be non-Gaussian. So you need to look at advanced data techniques. And people are considering not just a Samocam filter, but looking at the particle filter. It's still early days. You need to preserve water balance, which is something you just include a balance term in your, for example, in your penalty function. Okay. Another issue is that it's actually, in some parts of the world, not least where I live, in Norway, it's actually very difficult to make measurements of soil moisture, for example, from space. All the things that that actually do impact the measurement of soil moisture, in this case from SMOS, Soil Moisture and Ocean Salinity Instrument, it's an ESA instrument, the soil moisture, so this is a relatively dry orange, blue is relatively wet, occur in Norway. So you have forest, rocks, moderate topography, strong topography, wet snow, and open water fraction. All these things impact Norway. And in fact, it's a big challenge to try and make sort of sense of satellite observations for so much for Norway. We're doing that, and in fact, we're finding that it's not doing too bad. For those who maybe more have a British background, if you remember the Hitchhiker's Guide to the Galaxy, I don't know who's read that, but there's a character called Slarty Barkfast, who he's sort of thing he's proudest of is that he designed the Norwegian fjords when he designed the Earth for the mice. Well, my point to him is that when you were doing that, you were really not helping people making measurements of so much from space. So you should have done better. Anyway, it doesn't end there, because there are a number of issues with soil moisture observations. What I said before, in situ data, point measurements, and satellite data representing a greater area. So resolution typically 40 to 50 kilometers. So there's an error of representativeness in the horizontal, which you take account of. But it doesn't end there. Microwave measurements, some from space, are only sensitive to the first centimeters of the surface layer. If you look at L-band from SMOS, it's about 30 centimeters. With the C-band from ASCAT, ANSRE, it's about 1 centimeter. If you look at X-band, it's about a few millimeters. And in situ network, for example, in Norway, measures soil moisture to 10 centimeters. So one question is, what is being measured? What do we say is soil moisture? Is it the top few millimeters, the top 5 centimeters, 10 centimeters? What is it? And there's actually a debate in the community as to what do we mean by a soil moisture measurement. In fact, what one would like to do is to match those scales and integrated quantities. Perhaps if you're looking at the top 5 centimeters, what you're actually doing is, in some sense, doing an average of the soil moisture over that layer. One way of doing that is through a model or using data assimilation. But there's an issue about actually what is being measured. So some sample results. This is the only one I have that I'll show. I've got others, but this is ensemble common filter, which we're using at NILU against the extended common filter. The extended common filter is basically an adaptation of the common filter where you take account of nonlinearities, at least mild nonlinearities. And the extended common filter actually was used at Met France, and I understand now that ECWF are using it as well. So we have, this is amino acid for July, the sample common filter with 5 members. So basically dry is orange, wet is blue, and that's the extended common filter, that's the difference in percentage of between the ensemble common filter and the extended common filter. I mean, what I want to convey here is that we're not doing badly. There's some differences, but basically the difference between the method we have and the method that Met France has, it's very small. So at least as a first step, we're doing the right thing. Now what we want to do with this is to sort of then try and look at other periods, look at, say, for example, time series of particular place, look at sort of monitor soil moisture, and try and get a better handle on what the state of soil moisture is in the land. I mean, that's not just useful for science, it's useful for numerical weather prediction. If you get a better handle on the fluxes between the land and the atmosphere, you're likely to get better forecasts. Also this information is useful for hydrological sort of modeling and so on, and looking at monitoring some floods or droughts. Believe it or not, in Norway you do have some droughts as well, but more like that floods. Okay, so I've spoken about chemistry, future emissions, and land. There are many other applications, but this is 3 things I want to mention. Well, basically 2, but one has got two elements about what is happening recently. And the first 2 come from recent algorithm developments in numerical prediction and the basic concern how to represent errors. And these were based on presentations made at the IAMAS conference in Davos in July 2013. So what people at the Met Office are doing are they're trying to combine a variational approach with an ensemble approach. So the variational approach basically has like a fixed climatological background error confidence matrix, and the ensemble looks at the flow dependence of the errors. Okay, so in doing that, they're finding that you can do better. In fact, there's some papers by Craig Bishop, I think in Monthly Weather Review, where he actually tries to sort of derive a mathematical foundation that's based on sort of some rather interesting PDFs, basically the inverse of a gamma function. But the people want back in given the presentation by Pring. From ECWF, Roberto Buiza talked about basically ensembles, and one of the things they're doing is ensembles of data simulation systems. So it's not just ensembles of the model such, but actually the data simulation you're doing several analyses. And they're going to do that also to integrate, not just the atmosphere, but other elements of their system. And again, that is in the presentation by Roberto Buiza. Okay, so that's very much about how to represent errors, looking at, and this is actually a very important aspect of data assimilation. But I'm going to mention a potential new application, which is outside traditional areas, and looks at the citizen observatory concept, which takes advantage of the fact that a lot of us, all of us, have a mobile. And in the European Union, the Commission is very keen on this concept. It's a good point that they have funded at least 5 EU projects, one of which is Citizens, which I'm involved with. And that's the website. And in fact, I gave a presentation about this at the Green Week in Brussels in June. The idea is that at the end of the day, you're interested in information that impacts you. You're in the street. And there is much better if you have the information that is in situ. That in that street, this is going to be what the temperature is, or the next street you go to, whether it's raining, or whether there's a high pollen count event, or something like that. So it's no good that perhaps you're getting from the weather forecast or the air quality forecast that there is high ozone over a 3x3 square kilometer grid. Okay, so it's not quite relevant to you as an individual. So the point is that if you have a mobile phone where you can send data where you are and receive data where you are, you can then participate in sort of gathering information and receiving information at the citizen level. And I think also called crowdsourcing, I think. And in fact, today I downloaded a paper from GRL where they're looking at mobile, I think it's Androids, and using their information to look at temperature. Okay? So my understanding is that this is actually quite a interesting development and one big test of data assimilation ideas. But there's some challenges. One is visualization. You need to convey to the user information, whether it's high temperature, low temperature, and hopefully with the errors. And how you do that pictorially, that's not easy. There's something called infographics, which people have discussed in the literature, and it's a clean way of conveying error information to users. And that's likely a way of going forward. You also look at the models. You need to sort of look at models that look at sort of street level. You also need an algorithm, because if you want to combine that information perhaps with other observation pieces of information which have a different temporal and spatial scale, you need to take account of that. And privacy, and here, I started earlier with the numerical sort of systems association, but I think privacy actually here is very important. If you're using someone's information of where they are in the mobile, you have to be sort of careful that they are willing to give you the permission to do that. And that's in fact a big discussion in the citizen observatory concept of how we deal with privacy. In fact, to motivate that, citizen observatory is that most of you that have a mobile phone, you don't really use it to make phone calls. You use it to do a number of things, but perhaps not phone calls. So this is a growth in mobile use, it's a change in mobile usage, and it's an increasing range of features. And these statistics here show that the number of people in the world that have some mobile phone, that for example by 2014, mobile internet should take over desktop internet usage. A lot of searches we do are on a mobile device. So on average, Americans spend 2.7 hours per day socializing on their mobile phone. Have you done that today? I don't know. So that's over twice the amount of time they spend eating, and a third of the time they spend sleeping each day. The point of this is that the use of mobile phones is ubiquitous, and this is an opportunity to have an observational platform that can provide a lot of information that is useful to you and me, the citizen, at the level we're interested in, which is basically the street level. Okay, with that, I'll pass on to something, which is what data assimilation will do for you. Now, I don't know if any of you, I'm sure some of you have seen Life of Brian, and remember the famous line as to what did the Romans ever do for us. Is anyone not aware of that story? Okay, everyone's aware of that story. Well, I've transposed this to data assimilation. So, you might think I'm joking here, but in the last decade or so, I've been to meetings with people who work with observations and with models, and they want to know, why are you talking about data assimilation? what are you doing to my observations, to my beautiful observations that I understand very well? You're mixing them with a model. Why are you doing that? What's the benefit of me? Or someone with a model. I know my model well. My model, I can run it, and it gives me these forecasts that are fantastic. Why do we need data simulation? So the question is, what did data simulation do for you? And in fact, it does a lot of things for you. It provides you the analysis, the best estimate of the state, process size of climate studies, the initial state for forecast for numerical prediction or air quality. It allows you to evaluate observations and models, error assumptions and bias. It allows you to do data monitoring. I haven't shown that. But it can, certainly, I know at least in one case, people working, I think, at GMAO, I found that they found out that there's something had changed in the satellite I was measuring ozone, and they did that through data simulation, through monitoring the statistics between the difference observations and the forecast. You can quantify, do quantification, estimate changes in quantities and estimate transport, look at the impact of current observations, OHCs, observations, experiments, meta-agencies, and you look at the impact of future observations, OSSCs. So Eric Idle asks, what did data simulation do for us? John Cleese says, well, it got me talking to you. And Michael Palin says, beautiful Norwegian blue over there. And again, there's another element here that you know your Monty Python, you recognize that. There's a famous sketch to do with the parrot sketch, where, in fact, the parrot is dead, but I think Michael Palin is trying to sell this parrot to John Cleese, and in fact, the parrot is blue. It's a blue Norwegian, and it's pining for the fjords. And I happen to live in Norway. Okay. I think, hopefully with this in a, slightly humorous vein, I have conveyed to you that data simulation does a lot for you, for other people. Give you some idea of your motivated data simulation in terms of your observations have gaps in space and time. You need to fill them. You need a model to do that. How you combine the observations and the model, you can do that through data simulation in a way that has a mathematical foundation. Data simulation actually does a lot for you. It has some sort of potential sort of benefits in things like the Citizens Observatory and maybe others. So my last slide, except my extra slides, are that facts are not enough. You can read the quote. This is the opening paragraph of Hard Times from Charles Dickens. Thank you very much. Yes? Ooh. Well, it is arguably it's an art. I mean, that's, the three main errors that you would want to include. It's the so-called background error, which is akin to the errors in the initial conditions, and the number of ways in doing that. This so-called NMC, now NSET method, which you compare a 24-hour forecast against a 48-hour forecast. But sometimes they often have to scale the difference. There's the ensemble methods, for example, like ECWF, and so on. But then you want to do other things. You want this error covariance measure to be close to diagonal, so you need to choose carefully your variables. You do some other manipulations. But it's, how you do that. It's an element, there's a lot of elements of art and experience. So that's the background error covariance matrix. Then the observational error covariance matrix, typically people assume is diagonal. It's not always diagonal. And that's one of the reasons why I think people in numerical evaluation centers use radiuses rather than profiles, is that I think this assumption is better to use radiuses than profiles. Then there's the model error, the Q matrix that came into the common filter. And that often is just parameterized. It's a research thing. So there's that. Then there's bias. The equations, everything assume that things are unbiased, so there's bias. So what do? Often you start saying, well, I assume it's unbiased, and then try later and find out whether that assumption is consistent with the results I get. Or what also happens is that you include in your simulation process something that allows you to estimate the bias. And a lot of papers have been written on doing this. And the Met centers like ECWF spend a lot of time trying to evaluate how to estimate. So, and also you want to choose, another example is if you look at water vapor. I think it's relative humidity. Correct me if I'm wrong. One of the variables that you could use is less Gaussian. So you typically change to another variable that's more Gaussian. So all these things have to be taken account of. But it's, in some respect, yes, it's an art. And it's sort of means you have to be very careful with what you do, and you have to be also very careful in evaluating what you do. Oh, it's one behind you, Federico. Well, yes, I get you're right. It's difficult. I mean, you have to include, for example, precipitation. If you're going to do, if what we do, okay, what we're doing is, in this case, we actually have an offline model. So we're forcing with the atmosphere. So you need to get the proper forcing. But one of the things that you have to take, you say about precipitation, you have to take account of that. For example, if you do an ensemble common filter, you have to perturb the precipitation as well. So, but if you don't get the precipitation right, you're likely to not get that right. The other thing was the different scales. Is that right? Yeah. Yes. The land is much more heterogeneous than the atmosphere, and you have to take account of that. And you have to. There may be things that you may have to parameterize. Yes. I mean, the best models that I think are, in terms of resolution, of the order of 2 to 3 kilometers, which is maybe fine in the atmosphere, but in the land, it's certainly things can vary finer than that. So these are issues that, yeah, have to be taken into account. So that makes it the land much harder than the atmosphere. Yes, definitely.
So you mentioned at the start through the example of ECMWF perhaps having a somewhat better WP system than everybody else.
It's a provocative statement.
It is. So it begs the question, I mean, if a forecast system is understanding observations, developing models, and we have a good data simulation system, which of those would you put your resources in if you were going to do your forecast?
I asked this question once to Andrew Lorenz. What did he reply? No, what is the most important thing? Okay, all are important. I would possibly say improve your observations. Get more observations. Get more observations. Yeah.
Or improve your understanding of it.
You need to do everything, but is it a binary choice, one or the other?
Absolutely
not. No, I think you need to do all these things. I mean, I would say that ECMWF are not. It was not just data simulation. Better data simulation process, sort of algorithms that gave an improvement to their system. It was a combination of better modeling, higher computing power, more observations, and better use of observations. So all those things are together. If you were to spend your money, I mean, so models are relatively cheap compared to observations. So you can argue I'll turn it around. If your model was very, very good, then you might be able to get away with having less observations. But the model may not be very good beyond certain timescales. So it may depend on what timescales you want. I think at the end, it's a mixture of all these things. And I think it'd be wrong to say that it was just data simulation that gave that 2-day improvement in the forecast.
Any more questions for them? Then we'll try to ask if you want to go.